The Plateau Rayleigh Instability by Garrett Stubbings. So what is the Plateau Rayleigh instability? It is how a cylindrical jet of water basically becomes unstable at a point and turns into these discrete spherical drops. So in this video I'm going to go over an analytic look at the stability of the cylinder and how we get away from it, essentially. So how do we get to this analytic solution? We assume that it's a high Reynolds number in viscid flow and that body forces are negligible in our look at the radius of the jet. So in looking at that radius, we're assuming that it is just a perturbation around the base radius, which is whatever radius the flow comes out of our tap or whatever with, and it has some perturbation. So it has, essentially we're assuming that there's going to end up with some real positive instability term, and that it's going to come out of essentially this sinusoidal perturbation of our flow. So it's not going to be a perfectly uniform cylinder, and that there's going to be some interaction between these two leading to an instability. So the actual solution goes much like we've seen in this course, which is you go into your cylindrical coordinates and you have a look at your UR and UZ, and you basically just tack on your perturbation to those two components, and then you're also looking at pressure, which has the perturbation as well. So they all have these big R, big Z, big P, and then the perturbation, and they're all radially dependent exclusively. So then you can go into your Navier-Stokes equations down here and solve for the R and Z components, and essentially you only have the acceleration of those components equal to the negative pressure gradient over the density. You're throwing away the spatial component of your convective derivative, the body forces and the viscous forces. And then you plug in your solutions from, your proposed solutions above into these equations, and you end up with these two relations between the capital R, Z, and P. And importantly, since both R and Z are related to P, you can relate big Z to big R by taking the derivative of this second equation and throwing it in here, which gives you this relationship here, which is going to be helpful later when we're solving for R. So we've used Navier-Stokes. Now we use the other equation, which is the continuity equation, conservation of mass, and we're in radial, what is it called, cylindrical coordinates. So you have, unfortunately, the product rule for the radial component. Yes. And then you can plug in your proposed solution equal to 0, classic, and then you take the derivative with respect to R because we need to get rid of this Z, and the way to do that is taking the derivative with respect to R. So yeah, you end up with this di-Z di-R term in the back, another ugly product rule, and then you eliminate the di-Z di-R with this relationship, and you multiply by R squared, and you end up with this here, ODE, which should look familiar. It's the Bessel ODE with solutions which are modified functions of the first and second kind. So it's C times I1 of KR, this is a small r, plus D, I think it's big K1, but this one diverges at 0. Yes, so it's only the modified Bessel function of the first kind that's going to be applicable, because the second kind diverges at 0. So anyways, you continue with your solution where big R is this Bessel function. So what you do then is you look at your boundary conditions which is just the balance between, well, first of all, you have the velocity of this boundary, which is just given by your perturbed velocity in the radial direction. And importantly, you're balancing the forces between your surface tension and your total pressure. So your total pressure, you have like P naught plus your perturbed pressure. And then this surface tension term, which you just use the curvature to relate those two. Oops, equals 1 over R1 plus 1 over R2, which are the radii of curvature in the z direction, which is this curvature. And then in this, if you wanted to find the azimuthal direction, also has a radius of curvature. So this z direction, you end up with this this k dependence, which is your wave number of your perturbation, which is determining how curvy this bit is. And then the other part is just the radius of your cylinder, essentially. So the curvature of your this, depending on the wave number, gives you this kr squared, and then you have a 1 out front from your radial component of the curvature. And that basically gives you can relate that through a little bit of algebra to the solution of the real part of your exponent in your radius growth. And you see that for k times r naught, which is your base radius, that if k times r naught is less than 1, and I should mention greater than 0, then you have a positive real coefficient in the exponent in front of your t term. So you have a exponentially growing radius. So your cylinder is unstable. So there you go. You end up with an unstable cylinder, which is no good if you want to keep it a cylinder. But it's pretty cool that you can find an analytic solution to this, well, at least some aspect of this problem. So filming this turned out to be a bit of a hassle, because essentially, since your exponential growth is dependent on radius, you have to have a really small jet or stream or whatever. So I broke a pen and then shot some water out of it, and then you have this cylindrical area here, and then you have your individual droplets later. And how I did it was I just squeezed some water out of this Ziploc bag with my pressure applying device and my angling device into my sink. Worked okay. So I took the assumptions verbatim and assumed that it didn't matter which way I orient my apparatus. So if I go straight up, directly opposing gravity, which of course doesn't matter according to the assumptions, then we should still see a cylindrical section, and a deviation from the cylindrical section, and these discrete drops, which is what we see. It does look a little wonky in this way, though, but it does help with dealing with the trying to film a very fast-moving stream of water, which was somewhat successful. So I did try to get closer to vertical. Completely vertical was just not doable, frankly, with the with my apparatus. So I went at least partially horizontal here to hopefully get a clear view. And with this one, I tried to identify the individual droplets instead of just seeing some noisy things like you saw at the start of the video, which means trying to move my camera at the same speed as the droplets of water, which is partially successful sometimes. But you do see the characteristic cylindrical bit, and then later down the line these individual droplets, which hopefully you have seen. But yeah, so this is the Plateau Rayleigh instability in in action. Now, I will add the disclaimer that I'm a filthy theorist, so yeah, don't hate my experiment. I should also note that I owe MIT OpenCourseWare for the derivation, which I can provide you with upon your request. Thank you very much. This has been my video on the Plateau Rayleigh instability.